water flowing through porous media systems. And in the last class, we kind of argued and came up with an expression which is R okay. And I'm using a partial derivative here because later on as we go along, you will see why it is partial. But it's basically the first derivative, right? Delta H by delta X tending to 0 is basically the first derivative, okay? And this expression is kind of the cornerstone of groundwater physics, which is called okay. And this was as last class we talked about. This was actually formulated by Henry Darcy, who actually happens to be a civil engineer. For solving an applied problem, he actually formulated this law to solve water treatment problem, filtration problem. Okay, and this is what we call it as a hydraulic conductivity. Okay, and the dimension is length per time, like meter per day. Okay. And we looked at a few numbers, like sand is about 1 to 10, beach sand is about 1 to 10 meter per day, clay is low, coarse sand is higher, and so on and so forth. This is known as hydraulic gradient. Okay. This is delta H by delta X, length and length, so it's dimensionless. So purely from a dimensional point of view, Q happens to be length per time. Okay. Okay. And Q is called Darcy flux. Okay. And so purely from a dimensional argument, if I look at, if this is length per day, this is dimensional, this becomes length per day, which means the unit of Q should be like meter per day or something like that, right? Now, if you look at a textbook, they actually say that, okay? So I'm going to kind of deviate from the textbook. This is kind of important, and say do not use, even though this is right, mathematically and physically right, we are not going to use this unit for Q. And I'll tell you in a minute why, okay? We are going to think of Q slightly differently. Okay, we are going to think of Q as a flux, a little more physically. Okay, what's the definition of flux? Have you come across this word called flux in any other classes? What is flux? Flux of something means what? Can you think about any other flux? What if we think about like a radiation, solar radiation, flux of solar radiation coming to Earth? Okay. Flux by definition is defined some transported quantity. Okay, there could be momentum flux in a nuclear reactor. There could be a neutron flux. If you talk about solar radiation problem, there could be a radiation flux coming into the system. Okay, flux by definition, or thermal flux or heat flux. Okay. So flux is a fundamental transport property, which comes in fluid mechanics, thermodynamics, and all these things. Okay. Flux by definition, a generic definition of flux is the amount of a quantity, a thing, if you will, which is, in this case, the thing is a transported thing. Transported phenomena crossing area per unit time. This is a general definition of flux. Okay, it really nothing to do with Darcy's law at all. It's actually a transport phenomena definition. Okay. A flux by definition it's something crossing unit area per unit time. Okay, So let's look at a very simple problem. Let's look at pipe flow. There is a water flowing through the system, which is cubic meter per day, right? Q. Okay, and there is an area associated with it. Okay. Okay. So if you look at this phenomena, and the minute you talk about flux, it's amount of something crossing unit area per unit time. So the flux is always associated with something, okay, and that thing could be a volume, mass, or heat energy, whatever it is, okay, crossing unit. So it's always associated with the control area too, okay. So in this case, what is crossing? It's the volume of water, right? Crossing, and this is the control area. So it's like a vector quantity actually. It's got a direction, and then it's normal to a surface. Okay, so this is my area. Okay, so in this case, the basic flux will be water flux, which is cubic meter of water crossing unit area per time. Okay. So what is flux in this case? Well, it's nothing but Q by A. Okay, which we actually call it as velocity. Remember, typically we call it as V. Q by A is V from a continuity, this thing, right? But here I'm not going to, well, how does it come? Because this is cubic meter per day per meter squared, right? And we cancel meter squared, and this will be meter per day, okay, which is fine. That's a velocity, okay? But more fundamentally, it's actually a flux. If you don't cancel it, it has this, so which is amount of something crossing per unit area per unit time. So that is the area here. Okay, that's a more fundamental way to define a flux actually. Okay, and you will see in a minute why I define, because in case of open pipe, there is no difference between V and a flux actually. So in this case, Q is nothing but Q divided by A, which is also V is equal to Q. This is for open pipe. Okay, so the flux is nothing but Q by A in this case, and velocity is also happens to be Q. I can cancel it and it works out just fine. Okay, so but now let's look at in terms of porous media. So we take the same tube, if you will, right, a little column, and fill it with porous media. Okay, so let's now I don't want to erase this. Okay, so for porous media, so let me take this out. So for porous media, for a porous media system, the idea is still the same, okay, except now my column is actually filled with oil. Okay. Now what if I push the same amount of flow through the system, just like an open pipe? Let's say I'm going to push same amount of the flow to the system. Okay. And now I'm going to define this A, this as A. Remember, A is the bulk area. A does not change. A is nothing, same A. Okay, so I'm going to keep the same A. Now if I define Q is equal to Q by A is the Darcy flux, which is nothing but cubic meter of water, meter squared, per time. I'm not going to cancel the units, and there is a reason for it, because a flux is when the minute you say flux, you got to associate with some quantity and some area to it. Okay, so we're going to keep this unit always. Okay, so Darcy flux in this case is the total flow rate divided by area. Area is a total area. So here's my column. I'm going to assume the entire area. Okay, but does the flow occur through the entire area? No, right? It's only occurring through this little porous space. So what is the true area? So if I look at that face, okay. Now if I call this as area, okay, what is the true area there, which is actually transporting? Porosity. Okay, there is only a fraction. So the true area is, or well, if I can call it as a true area, so-called true area, is nothing but A times porosity. Okay, that's where the flow goes in. Okay. Now, if I use the true area, then I'm going to call it as a V. So Q divided by N times A. Okay, which is also nothing but Q divided by N. And now, okay, although dimensionally it's same, now I'm going to call it as a meter per day because it's a velocity unit. Okay. So dimensionally it doesn't make difference, but physically it makes a lot of difference. Okay. So one is a flux which is associated with the flows, the other one is a velocity. Okay. So if I deposit, let's say, well, let's pick some numbers. Okay. Let's say we solve a problem. So I'm going to come up with some random numbers. So here's my column. Let's say I take a 2-meter column, okay, and push, I don't know, I'm going to make up something, 1 cubic meter per day. Okay. And the area of cross section is, let's say, I don't know, point. I'm not even sure that those things will make sense, but let's go with that. Okay. So that's my pipe to start with. If it's an open pipe, scenario, Q is equal to Q by A, which is 1 divided by 0.1, which is equal to what? 10 cubic meter per meter square per day. Okay? And open pipe, V is equal to Q is equal to 10 meter per day. Okay? So if I dropped a blue dye here, how long it will take to exit in this open pipe? 0.2 days, right? So if I dropped a blue dye, transport time, if I drop something in the inlet, how long it will take for the particle to move, right? So the question is how long it will take a particle to travel this column or travel this pipe. Okay. Well, V is equal to dx by dt. Okay, so dt or x by t. So t is, I always need to, so t is equal to delta x by v, which is equal to 2 divided by 2 meter times 10 meter per day, which is equal to what? 0.5? 2 divided by 10? No, 0.2. Okay? So V is what controls the travel times. Okay? Now, let's do the same for same thing. Well, first of all, what is the intuition? If you repeat the same thing and fill the column with porous media, how long will the particle take? Will it go up or go down? Arthur?
How long will travel time take?
Yeah, I do the same experiment.
Travel
Okay.
time should take longer.
Travel time will take longer. Long? Short? It can change. Okay, next.
Same Q.
Same Q, everything's same, except I filled it with sand now, or glass beads. Shorter? Shorter? Longer, anybody? Longer? Short? Short? Why? Anybody, any long? Remember, majority can be wrong in this class. Okay, why is it shorter? Arthur, you want to change the word? Okay.
There's less area to travel through.
Okay, so why is it shorter?
Why? Because, I mean, we're multiplying the denominator by a fraction.
So the velocity will be higher, right? Okay, that's right, yeah. I mean, the trick here is, I mean, intuitively you might think, well, if I put the sand, it's going to have more resistance, more losses. Well, the trick is I'm going to push the same flow through the system, which means I'm going to put more energy. So the trick is, if I'm pushing Q through a pipe, it's going to take less energy. If I'm pushing so if you look at the head here, to push the flow through the system, I'm going to create enormous amount of head to push. So that's what I'm spending more energy now in the porous media system. But as long as if I said I'm going to push the same flow through the system, then it will take shorter time because you're pushing the same flow through a smaller area, so it should be faster, a lot faster. Okay, so let's put some numbers and do it. Okay, so here's my pipe. Okay, so this is my new model, but I'm going to push the same. So as a side note, if I connected a manometer here, and if the water level is somewhere here, let's say in this case, if I connected a manometer here, what would be the reading on the manometer? Will be huge, because I need. So if let's say this is 1 meter, this will be huge, 10 meter, 20 meter, whatever. So you got to put an enormous amount of energy to overcome the friction losses and stuff. Okay, so but if I push the same flow, then porous media filled pipe. Okay. So Q is equal to Q by A. So 1 divided by 0.1. So look at the Q's. Q is exactly the same. The flux does not, because the control surface is exactly the same. It's just an arbitrary definition, really. I assume a control surface is something normal, and I've not accounted for the flow. Okay. So and now the transport velocity V is equal to Q divided by N times A, which is also equal to little q by N, which is equal to 10 divided by, so let's, now you got to tell me what is N. We'll pull the magic number 0.4, which is equal to, what happens, 100 over 40. Can somebody calculate that for me? How much? 25? Oh, yeah. Okay. 25 meter per day. Okay. Again, the book calls that as a meter per day, but I'm not going to buy that unit. Okay. In this class, you're not going to do that. Okay. Now, transport time, if I calculate, T is equal to x by v, which is equal to 2 meter divided by 25 meter per day, which is equal to what? 200 divided by 25, 8? No? Sorry. How much is it? 0.025, right? 0.025? Whatever, okay. Yeah, okay. It's 25, let me. 0.8 days. Okay, so let's look at one of your homework problems. Um, It's good to solve these problems right away after the lecture. Okay, even though it's a fifth problem, last problem in the homework set. If a pipe is below is fitted with a porous filter of 3 meter long, a porosity something, intrinsic permeability is something. Given the water flow through the system, why don't you read this problem? So. So this is a little filter, if you will, a porous media filter, and this is an open pipe, really. Okay, given the water flow rate through the system, so Q is given. Okay, and when Q is given, if the area is known, I think the radius of the pipe is given, right? Radius of the pipe is this thing. Immediately you can find the Darcy flux through the system. Okay, and the key is the Darcy flux does not change whether there is a porous medium or not. Okay. So if there is a Darcy flux of Q through this open pipe, the same Q has to go through this too. Okay, but the velocity will be different. Okay, so when you release a dye here, it will go slow, and the minute it hits this filter, it's going to accelerate. Actually, it will go faster. Because that's the whole point. Okay, and then find the conductivity, and there is an equation we derived in the last class which connects. What is that? Permeability to conductivity, right? K is equal to Ki. What is the equation we derive? Rho. What is that? Rho G. Rho G by mu. Okay, yeah. So if I know the permeability, density of the water, density of the fluid, gravitation constant, and viscosity, I can find hydraulic conductivity. So that's another thing they want you to find. And then if the Q is known, Q is equal to minus K delta H by delta X. And if I given Q, given K, I can find the gradient. Okay, so that's pretty straightforward. So these are the three things you need to manipulate. Given Ki, find the conductivity for a different fluids. I might give an oil or. By the way, this is exactly the same equations used for filters in your automobile. I mean, if you want to find the flow rate through an automobile filter, exactly the same formula, really. They define a permeability of the filter media, and then for different fluids, you can calculate the conductivity. In that case, it will be oil conductivity. And it's the same law which governs, actually. So if I know the K, if I know the Q, I can find gradient. If I know the gradient and the K, I can find Q. So there are all kinds of problems around that. Okay. So let's do one more. Oh yeah, before we do, is that clear? Is that problem manageable? Okay, so that's pretty straightforward. So it's actually a very simple set of homework problem. The number 3 is actually given some. It's the same thing. Manipulate the Darcy's law, and then there is a lot of viscosity information given. So find for oil what happens to this. For water, what is the conductivity, and so on and so forth. Okay. And then the book problems are really trivial. So this should be a relatively easier. So this is for liquid, I mean water, and then I said if I use olive oil, what happens? Same problem with the oil conductivity. Okay. Yeah, we'll keep talk. Look, we'll come back and look at it. Okay. Now, before we go to the next topic, I also want to make sure that remember how did we come up with this so-called Darcy's law? Okay, and what is the law? And we call it as a, this is more of a philosophical discussion than anything else. Okay. So what is a law? When do we call something as, I mean, there's a lot of debate in the media, right? Evolution, is it a law or a theory, all that stuff. So as a engineer or a scientist, when you use a principle, what is a law?
It's a concept that the world abides by.
A concept the world abides by. Okay, you mean the physical world abides by. Okay, that's one way to look at it. Anything else? Which means it's truth. This is so the world basically sees when water goes through the system, it says, okay, I got to obey Darcy's law, so it goes like that, right? Okay. Do you buy into that, Arthur? Or when I drop we call Newton's law, right? When I drop a little stone, the stone's thinking, whoa, Newton told me that, so I got to accelerate at that speed. Is that so? You think the physical object senses the law and behaves that?
No, it's just an equation that describes the way of the world.
That's a big difference. Okay, we made that up. Okay, the physical world does not really conform to any law. Okay, we looked at the physical world when Newton saw the apple falling. If it's true, that story is true. It's not that trivial. Obviously, the man spent a lot of his time not just looking at the apple. So if you just look at the apple falling, nothing is going to come to your mind. Okay. He conceptualized it. Okay, that's why an origin of a law is it's actually a concept or a conceptual model. Okay, so law by definition it's actually a model of a reality. In this case, it's a mathematical model of reality. There are different types of models, physical models, mathematical models. In this case, it's a mathematical model of reality. Okay, so it's truly a model. What's the definition of model then? Is model right? Let's think about Newton's law for the matter. Newton's law is a model of how the physics of the world works. You think Newton's law is right? Yes, no? You think this idea that the bodies pull each other and based on that I can write F is equal to ma, is that always right?
More right.
Say that again?
More right than wrong.
More right than wrong, that's true. Okay. Now, the first thing is the definition of a model is an approximation of realities. Therefore, from that implies all models are wrong. In fact, there's a famous quote by a guy, Box, who is a famous modeler. He said all models are wrong, but some are useful. Okay, so Newton's law is kind of a useful model. Okay, and we know from Einstein, he threw away the basic tenets of basic Newton's law. Actually, I mean, in fact, he said gravity is a conceptualization of time-space continuum where things are warped, so it's an illusion really when the body goes through the system. Okay, it's just for a big objects it works. Okay, this simplified reality just works for the type of problem we solve, big objects. And they are not moving at huge speed too. I mean, but the minute you accelerate the object to close to the speed of a light, the law falls apart. Even some basic laws fall apart. Conservation of mass is a basic law we always use, right? What did we do? Mass can be neither created nor destroyed, right? That's a very basic. Is that true?
Not always.
When is it not true?
Mass change.
Well, when does it change? I mean, it's a powerful statement. Mass can be neither created nor destroyed, right? Conservation of mass is, when you put x kg of something, it's always x kg. It just goes to different phases and transforms and all that stuff, but you can track eventually the mass conservation is applied. Except you dropped a nuclear bomb on somebody's head. Okay, now you can convert mass into energy. So energy and mass are interrelated. E is equal to mc squared, right? So there's a little bit of mass defect there, and that's what is converted to energy. Again, the speeds change. But the bottom line is, when we say law, model, concept, it's very nebulous actually. Okay, as you start as an undergraduate, when somebody said law, you are kind of, okay, it's law, Newton's law, it has to be right. No, not really. Okay. For example, I mean, think about it. Do you know where the gravity comes from? Is it like something internally pulling like magnet? We don't know that. It's just a hypothesis, really, that the mass attracts each other. We don't know exactly how it originates or anything. And Einstein model was this. Now, I don't fully understand that, but if you think about it in a simplistic sense, he said time and space are connected and the space is warped, and so when you drop an object, it actually accelerates towards its center, and that we see it as a gravity essentially. But there is no physics going on there. I mean, if you can figure it out, probably you'll win a Nobel Prize actually, if you could go and make a measurement and show this is how the gravity is. Okay, so even some very fundamental concepts are based on these conceptual models. Okay, so when we say Darcy's law, you think it's right all the time? No. You think there is a conductivity which the water sees and the water and the soil particle sees, so that when the water goes, hey, look, there's high conductivity, I got to go faster. No. I just did some experiment. How did we come up with the Darcy's law? I do experiments. Right? I pack a column and make some measurements of flow. I can't really measure anything. I simply say, okay, how did we come up with the Darcy's law? We packed a column and kept increasing the volume, and we said there is a linear association, and then that constant, we slapped it as hydraulic conductivity. So this is to some extent, a made-up constant. Or we call it as a parameter. Or model. Okay. Now, the model becomes a law when a lot of people start following it. It becomes useful. Okay, we did this filter, we did that filter, we looked at soil, this thing, and they started documenting. Okay, so we said, well, soil, we know conductivity. There is nothing called conductivity, really. We came up with this linear relationship and said, hey, there is a constant, and we did many experiments and started documenting all this information. And then we kind of transitioned from this Darcy's equation into this so-called law. Okay, so keep that in mind. I mean, everything is open to question actually. Keep an open mind. Okay, so this is purely a model parameters, and you will see as we start applying these theories to real systems, there are real problems actually. Okay, there are issues. In fact, there are people question what is hydraulic conductivity in a certain system, and we'll talk about it down the line. Okay, and same thing with porosity. And also these model parameters are associated with what we call some sort of a control volume. Okay, and basically in this case we call it as these parameters are defined. They are defined over a representative volume. This is an average quantity, okay? So, for example, if I took a little one soil grain, is there a conductivity to it? If I take one little bead, either small or big, okay, I picked it up, can I say conductivity of this? Does it have a conductivity? Not really, okay? So in order to define conductivity, you need to have some statistical average. You need to have, I don't know, not 2 grains, not 3 grains, maybe 2,000 grains. You need a little bit of soil, which can be packed into a column, okay? So it is, by definition, is defined over a representative volume. Okay, if I take one big chunk of one tennis ball type porous media, there is no conductivity. So you need like maybe 10,000 tennis balls packed into a column, then there is a conductivity for the tennis balls. Okay, so there is a volume associated with it. The same thing with porosity. How do I define porosity? Well, again, if I take a 1 grain of soil, what is the porosity? It becomes rock actually. Okay? So in order to define porosity, I need to take, I don't know, 10,000 grains of soil, and then I say over that volume, there is a porosity defined. In fact, if you actually mapped, a porosity is a good example. I mean, this volume actually falls together. So if I mapped, let's say, volume of the sample, okay, so if and porosity. Let's say I take this much soil, okay, I don't know what is this much will be, 1 meter cube, okay, so I start from here, 1 meter cube, okay, and I measure the porosity, it's close to, let's say, 0.4, okay, so at 1 meter cube is 0.4, okay. Now I'm going to make this cube smaller. So it will kind of oscillate around this. Okay. Then let's say I come to 0.1 meter cube. Very similar. 0.01 meter cube. Okay. If I keep decreasing, what happens? Let's go very small. 0 zeros. What happens to porosity? If I take, so I'm taking samples at smaller volume, right? Okay. Now, if let's look at one extreme. Let's say my control volume is such a way that it's the size of the grain. What happens to porosity? What is the porosity of a grain? That's right. So if I'm operating as a grain size, well, it's really not 0. It's 0 or 1. It depends what my control volume is. If I dropped it and caught a single grain, then it becomes 0. But if I happen to sit in the pore, then it becomes 1 actually. So really the porosity will oscillate like this. Right? I'll catch a pore, catch a grain. So it could be 1 or 0. Boom, boom. Okay? And so it will actually oscillate. That will be the relationship. Okay? So when we talk about the representative elementary volume, that's the volume you're talking about. You need to sample sufficient volume so this oscillation damps out. Same thing with conductivity. You need to sample some sufficient amount of information from the system so that whole thing is and this is called the REV, or representative elementary volume. Okay, so by definition, these parameters are defined over certain statistically average elementary volume. Okay, otherwise they don't really exist. Okay. Okay, so let's with that. So that kind of nicely brings us to how do we measure conductivity. So, well, we measure conductivities using permeameters. At least in the lab. Okay. So what we do is we take a little sample, okay, and we seal it. So this has got the sample through it, okay, and then you create a little hole and put it to some sort of a head here. Okay, and here you have a graduated cylinder and you measure the flow. Okay, and the length of the sample is this. And you in your geotech you probably would have done this. Okay, so you force some head through the system. So what is so if I draw a line here, dotted line here, this is my delta H through the system, right? And that delta H is dropped over which delta L? That delta L, delta X basically, that length, right? You can view this other way around. You can actually view this as a column with, you can view it straight this way. Okay, and this is my L equal to delta X. These are exactly the same thing, right? Remember, that we already argued that the orientation doesn't matter. It's only the end head information. Okay. Now, what you do is you set a setup like this, either way, that way, or this way, and then you make some measurements. There's a flow coming through the system. So you take a beaker and measure the flow. So if I measure a certain amount of flow, then flow will be equal to volume per time. Okay, so this will say, okay, I measured certain amount of volume of water and have a stop clock, and that will give me my flow. So to measure flow. Okay, and once I know the flow, I can apply Darcy's law. So Q is equal to NSK delta H by delta X. Okay, and I know delta H, which is that head. I know delta X, which is that length, or Q is equal to what? Remember, that's Darcy flux, so Q equal to Q times A, right? So if I know the diameter of this thing, I can find A is equal to pi d squared. Okay, so I can now write this as Q is equal to K K delta H delta X, it's a minus sign, A is pi d squared. Okay, so I know the diameter of the column, I know delta H, I know delta X, I know Q, I can find K. Okay, and the negative will work out, it will be negative gradient, so you will find, I mean, basically it's a great, this sign comes, the flow is in this direction, so it will work out automatically. Okay, so from that we should be able to calculate the and if you want further, we can put Q is equal to V by T and all that stuff. Okay, you can figure it out. Okay, so that's a simple way to, this is called what is it called? This is called constant head permeameter. This method is constant head permeameter. Okay. So it's basically direct application of Darcy's law, right? Okay, and there is a second method. Well, for those of you who did the geotech experts, which there are quite a few here, when do I use constant head permeameter? There's another setup is called falling head permeameter. Let me The falling head permeameter has got a very similar setup, except you would have a sample, the pipe, inlet, okay. What you do here is take this out. This. Now here, this is constant. This is a constant head actually. Okay, so this is a constant head. Okay. So this delta H is fixed. In this case, it's not a constant head. You allow this head to drop. Okay. And in fact, what you're going to do here is, so again, it's the same definition, L. The head is basically defined from here, or head. Okay. Actually, to start with, this head will be H naught, and then after some time, it will come here. So we'll call it as H. Okay, so it's going to actually keep dropping. Okay, and the data you record is, and then this is the diameter of the tube. dt is the diameter of the tube, and then dc is the diameter of the column. Okay, so dc is the diameter of the tube, and then the idea is you let this head drop. Okay, and the data you collect here is the volume data. You just measure the volume, right? The flow rate. The data you collect here is you actually collect this drop, time versus H. So it will start with H naught and it will keep dropping. Okay. And somehow you're going to use this information to calculate the hydraulic conductivity. Okay. Now before we actually do that method, when do we use this? When do I use this, Richard?
The constant head is for really pervious material.
Okay.
And falling head is for less pervious material.
Why?
Because a constant head, if it
the answer was the constant head is going to use it for pervious material, which is like sand and something, and the falling head he wants to use it for less pervious material like clay, silt, and so on and so forth. Question is why?
okay, for the constant head, if you ran a falling head with like a sand, it would go way too fast. You couldn't even time it.
You couldn't time it. Okay. Yeah. Okay. The one question was, if I pack this with sand, it'll go so fast you can't time it. So it might have a lot more error. What if other way around? If I fill that one with clay, what do you think will happen? Can I run it? Yeah. Nothing will flow through the system. Why? Because you need huge gradients to drive water through a clay material. Okay. So if I pack this with the clay, think about it. If I pack this with clay, in order to drive some known amount of flow through the system, measurable amount of flow through the system, you need a column which is, I don't know, 10 meters or something. Okay. You need to put an enormous amount of pressure into the system. Okay. That's why, whereas here it can slowly drain on its own, okay, and then you are not basically, and you can just collect some data, and vice versa. If I put sand in the system, it'll drop so fast you can't get good data set. Okay. So in terms of analysis, what you do here is you basically just use. Let me derive it here. Use the continuity equation here, actually, literally. Okay. So Q in as a function of time is equal to minus AT dH by dt. Okay. So this is basically the rate at which the Q is going through the system. Okay, is nothing but the rate at which the head is falling, and it's obviously proportional and proportional to the area. If I have bigger area, there's more flow going through the system. If it's falling fast, there is more flow going through the system. Okay, and Q out function of time is equal to k area of cross section of the column h divided by L. Okay. This is straight from the Darcy's law, okay, which is nothing but Q is equal to Q times A, which is equal to K delta H by delta L times area of cross section. Okay, so basically this is Darcy's law. Okay, and they have to match. Whatever going out should be coming in. So minus A tube dH by dt is equal to K A cross section divided by L. K is equal to minus A tube A cross section L H dH by dt. Okay, and we know at t equal to 0, h is equal to h naught. At t equal to 0, t equal to t, h of t t is equal to sum h. Okay, now I can integrate this expression. If I integrate this, basically I can take dH by h and everything else this side and integrate it. I should get kt equal to minus at by a atl log of h plus c naught. Use the initial condition at t equal to 0. C naught is equal to AT ACL log of H naught. And substituting this thing, if you take this and substitute it, you should get it's in your book actually, the derivation, it's in the book, so it's pretty straightforward math. Okay, so essentially you take this and log transform it and plot it log h naught by h versus time, and you get a constant, and then from knowing this and this and this you can find the k. Okay, pretty standard experimental procedure. Okay, so those are the two methods. So one is for low conductivity material like clay, and the other one is for high conductivity material like sand. Okay, so that's how we evaluate the hydraulic conductivity in the laboratory. Now, if you never seen these permeameters, probably talk to. Are you guys teaching geotech lab? You're teaching. Talk to Sam, and maybe you can go and take a look at the permeameter in our geotech lab. We probably have both set up, right?
We'll have them set up 1 week coming up. I don't
Okay.
know what week it is.
Okay. Are you guys still measuring the glass bead conductivity? Are you?
I don't think so.
Okay, because you want to be careful with that. Okay, anyway. Okay, let's questions. Okay, so let's do a few more. A quick another example. Here's a example problem. Let's say I have a column which is set up this way, and this point is 3 meters, this point is 2 meters, this is 2 meter, And I think K is given. K is equal to 2 meter per day. N is equal to 0.4. Okay. Pressure at A is equal to 7357 Newton per meter squared. Pressure at B 19 Newton per meter squared. Or Pascal. This is also Pascal. I guess the first question is find Q. It's a little tricky and stuff. Actually, giving you the head, I'm giving you the pressure. So let's say I attach this to a pressure gauge, and that gave me the pressure, which I usually don't do. Okay, how do I solve this problem? Eventually, I mean, keep in mind all these problems. We're going to eventually use Darcy's law, right? So Q is equal to okay. So which means Q is equal to K H2 minus H1 divided by delta L, or length. And the gradient should be the other way around, so the negative will be gone. And then Q is equal to Q times A, okay? Which means I got to give you the area. Area is equal to 0.5 meter squared. Okay? Now the question is find H1 and H2. So what is the head here? How do I find this? Fang, how do I find the head over here? I have to, right? It has to be total head. What is the head here?
The arrow means the arrow is.
Yeah, the z equal to 0 here. What is Bernoulli's equation? P by gamma, or rho g, plus z1, right?
Yes.
Which is equal to P is A is 7357.5 times rho g. Rho g in gamma is equal to rho g. Rho is equal to 1000 cubic meter per kg per meter cubed times 9.81 meter per second squared. Okay, so this is 80 kg meter squared per second squared. Okay, so this will be P1 will be 7357.5 divided by 9810. Okay, plus what is Z1? The elevation height, right? 3 meters. So what is H1? By the way, this is roughly 10,000. So an easy way to compute in SI unit is this is roughly 10,000. So P by gamma is whatever the pressure in Pascal or Newton per meter square divided by 10,000. So it's about 0.7 something, right? So what can somebody give me the exact answer? I think it's 0.75. Am I right? .75 plus 3. So H1 is equal to 3.75. Okay. Similarly, you can find H2. P2 by gamma plus elevation at that point, 2 meters. Okay. P2 is 19,620 divided by 9810 plus 2 meter, which is equal to, I think it's 2 meters. It's equal to 4 meter. Am I right? Can you verify that? Okay. So H2. Okay. So first of all, which way the direction? Which is the direction of flow here? H2 is higher, 4 meters. 4 meter to 3.7. It's the direction of flow is the other way around. Actually, okay. So now from this you can find Q. K is given 2 times, and delta H is 4 minus 3.75 divided by 2 meter. Yeah, what is Q? Can you compute that for me? .25. What is the unit? 0.25 what? Okay.
Meters cubed per.
You got a 0 right away, okay? Because you lost the entire point of the whole lecture. It is meters cube per meter squared per day. Okay, that's a flux. Okay. Now find Q is equal to Q times A, which is equal to 0.25 times A is 0.5, which is equal to what? 0.125 cubic meter per day. Okay. So I can find my Q. Now what is my velocity? V. Velocity is given here. So V in the system will be the what? What is the unit there? That is meters per day. Thank you. Yeah, a question?
Basically, the flux divided by the velocity, right?
Yeah, flux divided by porosity. Oh, so we messed it up. Yeah. Oops. Yep. It's not Q by A. So mistake. Sorry. Thank you.
625.
Okay. Now, if I have a velocity, I can now ask questions. If I drop something, a ball here, what happens? It goes this way or that way, and so on and so forth. Okay. So that's kind of a direct application of Darcy's law. Okay. One last thing I want to talk about it is, the point here is, you given a pressure, you can go to head. Given a head, you can go to pressure. Okay. It's basically using this P by gamma, and gamma is, I mean, easy way to do gamma is approximately 10,000. Okay, so if I give everything in Pascal, you can just divide by 10,000. That will give you some estimate of. So before you do, I mean, when you calculate numbers, always to have an approximate estimate. So use that to come up with some approximate estimates before. So to make sure the numbers, like for example, if that's a Pascal given or Newton per meter squared, immediately okay, 10,000 it should be around 1.9. Okay, so then you go through the math and it's close to that you are fine, okay? And keep the units straight. We're going to stick to the SI units. We're not going to use PSI and atmosphere and all that stuff, okay? One last thing I want to mention is when we talk about pressures, there is an absolute pressure and a relative pressure, right? This is basically gauge pressure. This is the pressure which the gauge actually measures with respect to the atmosphere, and that's kind of important because let's say I have a let's go back to our McDonald cup here. So we got to talk about McDonald cup every day. So. Here's my Coke, right? And I put a little lid here, and I suck through it basically. Okay. So this is where your mouth is. I don't know. That's your mouth. I don't know, whatever it is. Okay, right? So how are you getting the Coke here? What is the pressure here? Negative, right? With respect to atmospheric pressure is negative. Okay, so the atmosphere is pushing here, and I'm just sucking vacuum really, right? Okay, so the question is, if I take my McDonald cup and drop it here and make a big straw, okay, would I get some Coke? It'll make suck a little harder. So if I want to pull the Coke up, I need to pull more vacuum into it, right? So I said, okay, I'm kind of lazy. So I designed a straw where I can put it from my room, my office, Harvard, to McDonald's. So whenever I want, I just call the guy, get me some Coke. He just drops the little straw there, and I can suck from my office. Can I get some Coke here like that?
You may need a pump.
I need a pump, right? So I got a pump there, and then so I put it in my office. So remember, my office is straight. This is my Harvard. This is McDonald, right? Okay. So I connected this, and I put a little pump there. I can turn on the pump, Coke flows, right? Okay. Now let's say my office happens to be Empire State Building, and there's a McDonald in the bottom floor. Okay. I put a little straw to the bottom floor. If I go to the third floor and turn on my pump, will it work? Fourth floor, fifth floor, to the top floor. You understand my question? So instead of Harvard, the poor me has become this big guy, and they put me in Empire State Building. Okay. Unfortunately, the McDonald's in the bottom floor. Okay. I'm a kind of a lazy guy, so instead of walking across, I don't want to take an elevator, so I got this magic straw which is connected to the McDonald's. So, and there's a pump here. Whenever I want Coke, I turn on the pump. Right? And so, well, I was in the second floor as a young engineer, it worked. Third floor, it worked. And I start going up in the corporate ladder. At some stage, will it work? It will quit working? Why? Will it work? If I go up, all the way up, I'm this vice president or president or CEO of this Empire State operation, and now turn on my Coke machine. It doesn't. Will it work?
You got the same pump.
I got the most powerful pump. Pump is not a problem. I'm the CEO, right? Get me whatever pump you want. I don't care. It'll be fine. But I'm sucking though. Remember that. So no matter how much ever I suck. So let's think about this problem. So this is the Superman, right? Super pump now. What is the maximum it can suck? 0, right? Vacuum can be 0. So you can't go more than that, right? So the pressure here, if I just use a vacuum pump, can be 0. What is the pressure here? Atmospheric. Atmospheric pressure is 101. So one atmospheric pressure is 101,325 Pascal, Newton per meter square. Okay. So if I put a 0 there, how high this pressure can push me? Around how much?
Around 10 meters.
Around 10 meters. I said 10,000 is your ballpark. So 10 meters is how many floors? Maybe 10 floors? No, maybe not even that, 10 floors. 5 floors probably. Okay? So if I go, as I climbed up the carpet ladder beyond 5 floors, my Coke machine is not going to work. You see that? Because that's basically your pressure over here. So P by gamma in this case is about 10 meters. Does that have application? If you had a lake house, the Great Lake House, and you have a lake in the bottom, and you want to take some water from the lake, okay? And if you have a vacuum pump, and you try to suck the lake from your top floor of the house, do you think the water will come? No. You can only lift the water using the atmospheric pressure is about 10 meters. That's it. So how do you get a water then for your Great Lake House? You got to push the pump from the bottom and push it up. You can create any amount of head. Okay? So I can now say, hey, McDonald guy, put the pump there and push the Coke up. That's fine. But I could never suck, no matter how hard more than 10 meter head, you cannot lift purely by suction. That's where the limit comes. It's also cavitation and all those things that will occur. But simply you cannot lift water purely by suction more than, which means in groundwater wells we don't apply vacuum pumps unless it's a very shallow well. We don't just suck water out. We actually put the pump inside this thing and lift the water. And lifting is fine. You can lift any amount of water to any amount of height. Okay, so you want to keep that in mind. And the last concept is when we look at aquifers, groundwater systems. So when you have, especially in the next problem-solving session, you'll see this. So if you have a ground surface, okay. So here's my porous media. There are two types of water-bearing system. One is as the rainfall occurred, the water just mounts, okay, and there is some rock here, okay, and these are known as unconfined system, and we'll talk more about it later, okay. But most of the problems you'll be seeing in the next class will be dealing with confined system, which is basically deep systems where there is some rock which is confining the water-bearing formation. Okay. So the water is going through system like this. So there is also another system. So this is unconfined. This is called confined system. Okay. A confined system will have a confining layer on the top of each other. Okay. So this is like almost like a pipe flow system, if you will. Okay. This is like an open channel system. But to start with, we are going to deal with confined system. A confined system is nothing but the soil column problems we just looked at. Okay. Just the top and the bottom layer, and the water is flowing through the system, in and out of the system. Okay. So initially, we will talk more about confined flow system, the problems we will be solving in the next class. And then we'll more talk about what's the difference between a confined system and unconfined flow systems. Okay, so let me stop there, and I'll see you guys, I guess, next week. But there is a lecture